Okay, we're going to continue working in Chapter 8, Section 2 with our proportions. And we've got a couple things that we're going to talk about, a couple neat things and a couple of So the first thing is our four-step process for a free response for confidence intervals. So our four-step process consists of stating what's going on. So what parameter do you want to estimate and what confidence level? So we're going to estimate the proportion of students who want to go prom with 90% confidence. So that way when you interpret later on, you know exactly the words you want to use for interpretation before you get bogged down in all the mess. So the next step is your plan. So your plan is identify your inference method. So our plan would be we're going to do a one sample confidence interval for proportions. One sample confidence interval for proportions. So that way it states that I know I'm working with just one sample. I'm doing a confidence interval and I'm working with proportions. So then I know what to use my proportion formulas. Okay, the next step is do. So this is all of our calculation parts that we can do if we meet our conditions. And I forgot to state it up here, but in the plan part, not only do we state what we're doing, so one sample, confidence interval for proportions, then we check those conditions to make sure that we can actually do it. And that way, if the conditions aren't met, then we don't go any farther. We just say, hey, it does not meet the normal condition, so I cannot make any calculations at this point. Or it does not meet the independence condition, so I cannot move on. And the last step would be to conclude. So after we make all of our calculations, we find our confidence interval, we interpret the interval in context of the problem. And that's when we go back to the state part and we say stuff like, I am 90% confident that the interval from 0.76 to 0.82 contains the actual proportion of students at Colony High School that plan to go to prom. Because all that came from my state part. I had a confidence level, I state what I'm doing, and I bring in that confidence interval. Now, everything we've done so far for confidence intervals has broken it down into bits. What is the point estimate? What's the z-star? What's our standard error? Z-star times standard error is our margin of error. And then we go through and we calculate all the bits and pieces. Why do we do that? Because a lot of times in multiple choice, they're going to ask you for those bits and pieces. One of the nice things is that if you work out bits and pieces, you can also check your answer on your calculator. So now, how do we check the answer on the calculator? How do we let the calculator do all the work for us? And that is, we use our stat button, and we're looking for a one variable z-interval for proportions. So that's like a one sample z-interval for proportions. So how do we do this? We go to our stat menu, we arrow over to tests, and these are all those statistical tests programmed into our calculator. So it's there for a lot of different ones. You just have to make sure you use the correct one, and it'll do all the work for you, and it's a good way to check your answer. Why don't you want to use that all the time? Because a lot of times on the free response, they want to see all those bits and pieces. And if you don't show them that stuff, you're not going to get full credit. So we go down to one prop z interval. So it's a one sample proportion z confidence interval. Z because we use z intervals when we do work with proportions. And we always use z's with proportions, and you'll learn that later. Then it goes through and it asks you for x. And x is the number of successes. So if I was sampling 50 people to ask about prom, 36 people decided they want to go to prom, so I'd put 36 here. Number of the sample, that would be the 50 people I interviewed. Confidence level. So confidence level, so if I want a 90% confidence level, I would put 0.90. And then you hit enter to calculate, and it will give you the interval in parentheses along with your p hat and n, and you have to show all that information. So if you're to use this to even possibly think about any credit, you're going to have to go through and write out all your stuff. One prop, z interval, on calculator, X equals 36 successes. N equals 50 in sample. C level 0.90. And then you have to report back what it says. Okay, my confidence level is 0.70 to 0.82. And then you have to tell me that P hat is really 0.76. And that, actually, that's not right. That'd be 0.72. But again, I'm just making up numbers and I'm showing you how you'd write it down. And then your N equals 50. And so you have to write all that down to show them how are you getting these answers. And they may or they may not give you full credit for that. It really depends on how they trained people to grade those. And sometimes they will and sometimes they won't, which really kind of sucks. But what's nice is you can do this on your own and check the answer of what you calculated. So if it lines up with what you calculated by hand step by step, it means you did it right. And it's a nice way to check your answer. So that way, oh, I know I did something wrong, I can go back and fix it. And if you have time, you can fix it. If you don't have time, then you're like, oh well. Okay. So sample problem. According to an article in the San Gabriel Valley Tribune in February 13th of 2003, most people are kissing the right way. What's that mean? Well, according to a study, the majority of couples tilt their head to the right when kissing. In the study, researchers observed a random sample of 124 couples kissing in various public places and found that 83 out of 124, which is 66.9%, of the couples tilted to the right. Construct and interpret a 95% confidence interval for the proportion of all couples who tilt their heads to the right when kissing. So first step is state. Now I put a lot of stuff in here for you, but it's to use it as an example because a lot of times this will be the problem that they give you. All of this is stuff that you are expected to write out. So what are we going to do? We're going to estimate the true proportion of couples that tilt their head to the right when kissing with 95% confidence. So it's really just stating what are we trying to do, so later on we know how to explain it. Okay, plan. We're going to use a 1, and you can write a 1 sample Z interval for P, or you can say I have a 1 sample confidence interval for proportions. To me, when I write it out like this, it makes more sense to me. That's what I'm doing. I'm doing a confidence interval for 1 sample for proportions. I'm good to go. And then we check our conditions, random. We had an SRS, a random sample of 124 people. So again, this is our N. Normal. We had 83 who tilt their head to the right way. That's greater than or equal to 10. And then how many did not? So 124 minus 83. 41, and 41 is greater than or equal to 10. So we are approximately normal. We have a simple random sample. Independent. Reasonable to assume. More than 1,240 couples. Okay, so now how do we calculate this? Well, we start by every confidence interval. We figure out our critical Z value. So our inverse norm, 0.025, which gives us a critical Z value of 1.959963986. Now keep in mind that when you're calculating confidence intervals, the more decimals you use, the more accurate your answer will be. If you round here and you round later, you're going to have bigger error, and you may be just far enough off that it doesn't really count. So this would probably be okay to round to 1.96, because this is really so close to 6 that it's not that big of a difference or an error. So you would be okay with doing that. Now, how do we calculate our interval? Well, let's start with our original proportion. 83 divided by 124. So 0.6693548,387 plus or minus that z value, 1.96, or you can use the full value, times our standard deviation. So what's our standard deviation? Well, it's going to be the square root of our original proportion, 0.66935 times 0.30645, and then divided by our sample size, which we found up here, 124, and that'll give us our standard deviation. So again, the more exact you are with those decimals, the better off you are. So when I multiply that, I get 0.2213. I divide by 124. Then I square root the answer, which gives me 0.042247. I times by the 1.96, which now gives me this 0.669. I'm going to go ahead and round to 0.67 plus or minus 0.083, which is now going to give us an interval of 0.67 minus 0.083. So our interval 0.587 to 0.67 minus 0.083, or plus 0.67 plus 0.083, 0.753, which means that we are 95% confident that the interval from 0.587 to 0.753 captures the true proportion of couples that tilt their head to the right when kissing. Again, this is matching our state portion, which is why we state that at the beginning. So if you have a trouble interpreting, doing that conclusion part, we go back to that state and it helps us out, which really means that about 58% to 75% of people turn their head to the right when kissing. That's all. Okay, so now we're going to take a step further because we have been working on those confidence intervals for a while, and we're going to talk about something related to the confidence interval but slightly different, and that is how to choose a sample size. So if you don't know how big of a sample size you want to use, we can use this idea of we may want to choose a sample size that allows us to estimate a population proportion within a given margin of error. So if you want your margin of error to be really small, you can do some calculations to figure out, well, how many people do you need in your sample? Because the more people you have in your sample, the smaller margin of error that you'll have, because the smaller our standard deviation is. So we can use the margin of error formula, which is this z star times the standard deviation. We can use that to help calculate our margin of error. So if we want our margin of error to be less than or equal to, and usually we want a less than or equal to for margin of error, we can set up this formula to help figure out what does our sample size have to be. Now, how do we know what p hat's going to be? Because we haven't done our study yet, so we don't know what p hat is. And so what we do is we can use a guessed value based on a pilot study. So someone did a study beforehand, very similar to what we want to do. We can use their proportion and our thing. Or we can use 0.5. Why do we use 0.5? Because that is going to give us the largest margin of error of all proportions. So it's kind of our keep safe value. That's going to be the biggest proportion that we could use to help maximize that margin of error. So either use like a 0.4 and a 0.6 from a pilot study, or use a 0.5 because that's going to be your safe bet. So sample problem. Suppose you wanted to estimate the true proportion of students at your school that have a tattoo with 95% confidence and a margin of error no more than 0.1. Determine how many students should be surveyed to estimate P within 0.10 with 95% confidence. So 95% confidence right away, I'm going to go ahead and think about that and calculate that Z star. So we're going to do an inverse norm. We're going to have an area of half of 5%. We're going to have a mean of 0, a standard deviation of 1, which is going to give us a Z star of 1.96. We're going to round for convenience sake. And then we have no previous knowledge, so we're going to use our safety net of 0.5 for our proportion. And we want our standard of error to be within 0.1. So my margin of error needs to be less than or equal to the square root, not square root, because I need my Z star, 1.96 times the square root of P hat, 1 minus P hat, all over my sample size. And so now I have an equation that I can solve for n. So how do we do this? Well, the first thing I'm going to do is I'm going to go ahead and I'm going to move this 1.96 over. So 0.1 divided by 1.96 gives me 0.051, less than or equal to the square root of 0.5 times 0.5 over n. So the first thing I want to do is, before I can move anything out, I have to get rid of the square root. So now I'm going to go ahead and square both sides. And that square will cancel out with the square root because they're inverse operations. So even though I have written down that I'm going to square this number, I'm going to square the full decimal on my calculator because it's still on my calculator. So now we're ending up with 0.0026 less than or equal to 0.5 times 0.5 over n. And now what I want to do is I want to get that n up above. I don't like having n on the bottom, so I'm going to times by n on both sides. So that way this will cancel because anything divided by itself is 1. So now I have a 0.0026 less than or equal to 0.25. Oh, I forgot my n. And now to get n by itself, I divide by this 0.0026. And I get that my sample size .25 divided by 0.0026, 96.1538. And actually, it's supposed to be greater than or equal to, so what happened here? Did I mess that up? Usually this should be greater than or equal to. I'm not entirely sure what I did wrong, but I'm not going to re-videotape this for after I figure it out. So my sample size has to be bigger than that because, other words, if it's smaller, it's going to give me a bigger margin of error. So I have to have greater than 96, which means I have to have at least 97 students in my sample. And so that allows us to sit there and finagle with things, knowing this in advance, to figure out what kind of numbers do I need to, how many people do I need to interview, instead of just saying, I'm going to interview 30 people. It gives us a good number to work with to have that good margin of error that we want. So we're going to go ahead and work on this in class. This is not something that you see a lot for checking for the number of students that you need in a sample or the number of people you need in a sample, but it is used. So we'll practice it.